All right, well, let's move on to our next topic of shear and moment diagrams. This is a continuation of these internal forces of members. In particular, what we're going to be talking about are beams. The difference between this and internal forces is what we want is a graphical representation of what's going on as we move from one side of the beam to the other side of the beam. Anywhere along the beam, say right here, I might want to know those internal forces, or here, or here, or here, or anywhere. And what we're going to have is we're going to develop these graphs so that we will show what's going on from one end to the other. And those are important for figuring out maximums, minimums, things like that. So before we get on with that, these are, instead of looking at frames or machines or more complex shapes, we're just going to be dealing with beams. And we haven't spent a lot of time talking about beams, so I thought I'd spend a minute and define. I know I've used this terminology before, but make sure we're all on the same page with this terminology. First type of beam is a simply supported beam. What that means is we have a pin on one side, roller on the other, and we have three unknowns, so we have three equations, we can solve that. Next is a cantilevered beam sticking out of a wall like we have here. Also three unknowns. In this case, all three reactions are on the one side. So it is also solvable because we have three equations from statics. Our next type of beam is a continuous beam. This is actually called a two-span beam. You could have even more spans, but with a continuous beam, we start getting into this world of statically indeterminate problems, meaning there's too many reactions for me to actually solve. In this case, you could count, I have 4 reactions with only 3 equations. So we won't really be working with these types of beams. When you get into strength of materials, we'll talk about how to solve these statically indeterminate. But if you hear the word continuous beam, you'll know what it means. Also, fixed beam means it's fixed on both sides. It's almost like cantilever, not from both sides. And you see we have 6 reactions, so definitely statically indeterminate. But we'll be focusing mainly on these top 2, simply supported and cantilever beams. All right, so let's talk about a beam section. So like we said before, we could look at an internal force on a beam by just cutting it where we want to know this internal force. And let's say we have a simply supported beam, which now we know is a pin and a roller, and let's put a force of 10 kilonewtons on this beam somewhere. Actually, I had it at the halfway point. Well, it doesn't really matter, does it? So not to scale, but we'll say it's 6 meters and 6 meters. And let's say we're interested in what's going on at some point here. We'll call this point A, and we'll say point A is, 3 meters from one side. Now we've done this with looking at internal forces. We said we could cut it at point A and look at those internal forces. By the way, the statics behind this, it is symmetric, meaning that 10 kilonewtons would be distributed to both sides. You could actually do some of the moments about one point or the other, but find that both reaction is actually 5 kilonewtons. So if I cut it at point A, I have something that looks like this. I have the 5 kilonewton force going up. Internally, I have a shear force that is going down, and I have an internal moment. There is no internal axial force, so I'm not actually going to show that. And this, of course, is 3 meters away, because this is our point A right there. So if I want to know those forces, I could say sum of the forces in the y direction equals 0. And then I have V is equal to 5 kilonewtons pointing down. And from sum of the moments about my cut is equal to 0, I would find out that I have, let's see, I have the moment. Now I'm still sticking with my same sign convention at this point. Counterclockwise is positive, and that's the way I drew that moment. So I have my internal moment, and then I have minus 5 times 3 is equal to 0, or that internal moment is equal to 15 kilonewton meters. And I got a positive number, which means it is actually going in that counterclockwise direction. Now, we also said as an alternative, what I could have done is I could have drawn the same section from the other side, and then I have 5 kilonewtons on that side. I have my 10 kilonewton load, and then internally I'm interested in what's going on with my shear force and my moment. So just like the other side, from sum of the forces in the y direction equals 0, I have V going up, minus 10 plus 5 is equal to 0, or shear is equal to 5 kilonewtons. But notice this time it's going up, not down. And sum of the moments about my cut is equal to 0. Same idea. let's see, our counterclockwise is positive, so actually I have minus that internal moment, and then I have minus 10 times, what is that, 3, and then I have plus 5 times 9 equals 0. So that gives me an internal moment that is equal to 15 kilonewton meters. Same answers as before, but now it's going the other way. So the question is, which one of these is right? Is it the moment going to the counterclockwise or clockwise direction? Is the shear up or is the shear down? Well, the answer is both are correct. It's all a matter of your perspective. Because of that, what we want to do is we want to develop a sign convention. And with this sign convention, it'll all be based on your perspective if you're looking from the left or the right. So our sign convention will look like this. We're going to call a positive shear as pointing down on the object on or the beam if I cut it as I'm moving from left to right. Now if I cut it moving from right to left, it's going to flip. And we know from Newton's third law, every reaction is an equal and opposite reaction. Both those have to be existing at that particular location. So in essence, they're canceling each other out. Same idea with the moment. So here's a positive moment. Notice I'm drawing it counterclockwise on the beam working from left to right. However, on the other side, I have a positive moment which is clockwise. And the easy way, I think, to remember this is to think about the overall effect on the beam. Meaning, and maybe you have a pencil in your hand or something you can bend. If I were to pull this beam up and create that moment in the direction that I have, that counterclockwise moment, you can imagine this whole thing would start to bend up. Well, what that makes is a big smiley face, and a smiley face means that we have a positive moment. Same idea on the other side. If I were to pull up on this side, I could see that they would create a smiley face, and a frowny face then would be a negative moment. So if I were to pull down on this side, or in the same idea, if I would have a moment which is going this way on the beam, it would make the beam frown, and it would mean that I have a negative moment. So with that in mind, let's talk about how to draw these shear and moment diagrams. Now there is a general process that I'm going to map out, and I will tell you that this is not my preferred method. I'm going to break this video into a couple different parts. I think or a couple different methods. This method is long and cumbersome. You probably won't have time to really use the method of sections if it's a long, complicated beam. However, it's good background knowledge when we start before we do the next video. So the way that I would start is statics for the reactions on my beam. And after I have the statics, what I'm going to do is I'm going to cut my beam at between each discontinuity. So what is a discontinuity? In essence, a discontinuity means that there is something discontinuous if I were to come up with a single equation for shear as I move from one end to the other, or a moment as I move from one end to the other. But in essence, this is where your discontinuities will be. It'll be at the beginning or the end of distributed loads. Could also be wherever you have a reaction, and in essence what we're saying is in the middle of the beam. We don't count a reaction at the very end of the beam as being a discontinuity because nothing's actually started yet. The third would be if you have any concentrated forces or moments along your beam. Those would be considered discontinuities as well. After I have those discontinuities, the third step would be to draw a free body diagram of that cut. And what you're going to be doing is you're going to be solving for your shear and your moment, and these may be in equation form. So we're going to say in terms of x when needed. More times than not it will be. And then the fourth step is to add these values to the diagram, or sketch out that shape, that line. So let's look at an example of how we put all of this together. All right, so for this example, what I have is a simply supported beam. I have these two 45-pound forces on this beam, and I'm asked to draw this shear and moment diagram. So we can talk about these parts and pieces. I'm going to label this A, B, C, and D, and that means I would have a reaction at A vertically like that, and we'll say we have a reaction at D vertically like that. There is a potential for an AX because it is a pin connection, but there's no horizontal force, so I'm just going to leave it out. Now what I like to do is work over on this side, and that leaves the space below my beam to draw these shear and moment diagrams. So in essence, in just a little bit you'll see, but what I'm going to be doing is drawing lines along here, and I'm going to have my shear diagram like say here. But we'll get there in just a bit. So the first step is to solve for these reactions. I'm going to sum the moments about A. What I find out is the reaction at D is negative 15 pounds, or what it's really saying is the reaction at D is equal to 15 pounds pointing down. And from there I can say sum of the forces in the y direction equals 0, and I end up with an AY of 15 pounds going up. So after that, this is that first step, doing your statics for your reactions. The second step, we said at each discontinuity, we want to cut between each discontinuity. So where are these discontinuities? There's one at each letter. So there's a discontinuity at B, and there's a discontinuity at C. Like I said, A and D are on the outsides, so those don't really worry about that. So first one that I'm going to look at is what's going on between A and B. And the way I do that is then I just draw a section as if I'm doing an internal force, and I put all my forces on here. So I have an external reaction of 15 pounds going up. There's no other forces, and this is like if I just were to cut it like that, right? And then internally, I know that there's a shear. Now I'm going to draw these as positive. Whether or not they are positive, I will find. But remember, a positive shear is down, and a positive moment is counterclockwise in this case. So let's start with sum of the forces in the y direction equals 0. I have 15 going up minus v going down is equal to 0, or my shear is equal to 15 pounds, a positive 15 pounds. And from sum of my moments about the cut is equal to 0. I have, now when I'm doing this, I'm still sticking with this counterclockwise as positive notation. So I have my moment minus 15 times however far away I am from the cut. So this is where I said it has to be as a function of x, right? I'm not looking at 6 feet. What I'm saying is as a function of x as I move from one side to the other. And this is my x distance. So I have a moment times, the 15 times the distance of x, and set that whole thing equal to 0. So I have an internal moment that's equal to 15x, and I got a positive value, which means it is counterclockwise. So we said that the next step would be to well, that was actually step 3, wasn't it? I don't know, somewhere around here. But step 4, let's add it to the diagram. Now I like to do this after each section. So I label my shear and I label my moment. Moments would be in pound-feet. And now to add these points, I say, well, all right, what about our shear at x equals 0? And this is all the way from A to B. So I think it's helpful to draw reference lines that we care about. In this case, it would be here and here, one at B and one at C. So going from the end of the beam out to point B, the shear is constant at 15 pounds. So I could just draw a straight line and label that 15. Now what I like to do is shade it in, make it a little prettier, get those extra points. I don't have to put units on this part because I put my units under the label, so I'm just putting it the one time. And then for the moment, what do I have? I have the moment is equal to 15x, so when x is equal to 0, my moment is 0. And then at x equal, well, this goes all the way until x equals 6, right? So let's say at x equals 0, my moment's equal to 0, and at x equals 6, my moment would be equal to 90. So I'm starting at 0 and I'm going up to 90, and I can see that it's linear, meaning it has to be a straight line. It would look like this. And I'm going to label right on here that this value is 90. So there's our first segment using this method of sections. Now let's move on to the next section. So next section would be from B to C. C would be my next discontinuity. So now we're saying, what happens if I cut it somewhere in here? what would it look like for these shear and moment diagrams. So start once again by drawing this free body diagram, and I have that 15-pound reaction, 45-pound force, and then I have my internal shear and moment, once again both drawn as positive. And from my sum of the forces in the y direction equals 0, I have 15 going up minus 45 going down minus v is equal to 0. From that I end up with v is equal to negative 30 pounds. And from sum of the moments about my cut is equal to 0, counterclockwise being positive. Then I have this internal moment. Let's see, minus 15 times. Now I have to think about, well, how far away is this? What is my x distance, right? So if I look at my free body diagram, I know that this distance from there to there is 6. And what I'm interested in is this being an x distance, right? Very sloppy. Let's see if I can clean that up a little bit. Hopefully that's a little bit better. So I have the 6 feet to the 45. Now x is going to be all the way from the 15-pound force. So I can put in those values. So from some of the forces in the y, I didn't change anything, but for some of the moments, it is important because that will be as a function of x. And in this case, let's see, what do I have here? I have minus 15 times this x distance plus 45. Well, what's this distance away from the cut? That would be x minus 6, surface auto scroll, and set that whole thing equal to 0. Now I have to multiply through, so I have what? Moment minus 15x plus 45x minus 270 is equal to 0, or rearranging this and combining those x terms, I get the moment is equal to 270 minus 30x. Well, all right, so I want to put this on the graph, so I want to know what's going on at my critical points, meaning I'm starting this at x equals 6 feet. And at x equals 6 feet, I know my moment would be equal to 90. You could plug in those values and see that. The other one I care about is at x equals 12 feet. At x equals 12 feet, my moment's equal to minus 90. And I can see that it's a linear function. It's not squared or anything, right? So to add those to the graph, let's start with the shear. The shear was just negative 30. So I have something that looks like, it's not going to quite be to scale, something like that. This is negative 30. And for my moment diagram, I'm starting off with a positive 90. Well, that's cool. That's where I left off with the last one. And I have to get to negative 90 by the time I get to this other side. And I know it's linear, so I'm going to draw a straight line between the two. Okay, one more segment to do. That's this last segment in between C and D. Let's draw a section between C and D. So I end up with a free body diagram that looks a little bit like this. Dimensioning it, what I know is I want to know this from this x distance away, once again from the very beginning, and I do know that this is 6 feet and this is 6 feet, and I don't know why my surface is acting like that. From here, just like before, sum of the forces in the y direction equals 0. I have 15 going up minus 45. Oh, come on, surface, we're almost there. Try this one more time. 15 going up minus 45 plus 45 minus v is equal to 0. From this, I get my shear is equal to a positive 15 pounds. And from summing the moments about the cut equal to 0, I end up with minus 50. Actually, let's start with a positive moment. Minus 15x plus 45. Just like we did last time, this is that first 45, and its distance away is x minus 6. Then I have that second 45. Well, that's going to create a positive, a clockwise or negative moment. So if minus 45, its distance would be x minus 12. And set all of that equal to 0. And hope your surface doesn't automatically add weird stuff in there. And then I'm going to multiply through, and I end up with something that looks like that. And I see that I have some common terms, this positive and negative 45x. Cancel each other out, and I end up with moment is equal to 15x minus 270. and put it all together. And just like before, what I want to say is, what about those critical points? I know at x equals 12 feet, my moment's going to be equal to negative 90 foot-pounds. And at x equal 18 feet, my moment is equal to 0. So finally I can add this last little section in there. And for my shear, I have positive 15 pounds all the way through. It's not dependent on my x. So I have something that looks like that. And for my moment, I start off at a negative 90. Looks like I dropped a sign there. That should be negative 90. And I'm starting off where I left off before, and I'm ending up at 0, and it's linear, so I get something that looks like this. So really, this is what I would be looking at for my shear and moment diagram. And like I said, now I could tell you, once I have this loading, what is the maximum moment that this beam has to support? Well, it has to support a maximum positive moment of 90, negative moment of 90, and a shear force of 30, or actually negative 30 pounds. So I hope that was helpful. Like I said, the next video is really, I think, a more efficient way to solve these problems. As you can see, this takes a while, and it's not a very complicated beam. So if you had a really complicated beam, this would take all day. So look for that, and or just skip ahead and do that one instead of this one, perhaps. All right, that one should already be posted. So good luck. Let me know if you have any questions, comments. I'll talk to you all later.